Hello and welcome to the OCR Cambridge National Level 1, Level 2 Award in Systems and Control and Engineering, R113 Electronic Principles. Now you've seen the opening video, or the opening title shot, which had a lot of components on it that describes sort of aspects of what we're going to be looking at over the next few videos. Each video is going to be about 15 minutes long. And then at the end of the video, hopefully there'll be sort of a challenge for you to go away and research something or carry on some additional revision. We're going to start talking about direct current in electronics. That's the sort of main type of electricity that we deal with, although you will encounter in some of your studies alternating current, but we're going to focus on direct current. I'm going to try and understand how that works. Now, I am interested in dealing with the exam paper. It's got 6 questions in it, and the questions deal with each sort of section of the learning objectives that you will have been studying. But before we even get into the exam paper, I want to sort of double check and revise some basic principles that we'll be using examples throughout. So to help you understand how the question works, you do need to be able to understand sort of the basic analogies that we're using. I have to give a shout out to Forrest M. Mims III. This is a fantastic tutor chap who's written these books. My copies are really old, by a company that doesn't even exist anymore, but you can still get work by Forrest M. Mims III if you go searching around the internet. His Getting Started in Electronics books is what got me started, and it's a fantastic resource for learning the basics of electronics. And I'm going to sort of plagiarise some of his examples because they are really good analogies that might help me understand, and hopefully it's going to help you. So what is electricity then? Well, there's no simple way to talk about electricity because we can't see it. I was going to say we can't touch it or feel it, but actually you can, because you can get quite a nasty shock from electricity. So it's something you need to be careful of when carrying out practical activities. Visualising it though, and this is an important thing, is to understand how a circuit works. It helps you if you can visualise how electricity actually as a concept moves. So I want to talk about atoms. And atoms basically have protons, which are positive, neutrons, which are neutral, and around them, this is a very sort of rough model, is the idea of an electron, which is negatively charged. And these happen in sort of, they say they happen in shells. In metals you have quite a lot of shells. But we're just going to look at, this is a helium atom, if that helps. Now we've got 2 positive charges, and we've got a negative charge here. I just want to imagine for a second that instead of having an electron, we've got a hole. That means that this helium atom is left positively charged, like so. If we had another atom here, there's 2 positive charges, there's an electron, there's another electron. Now that helium atom is neutral, it's neither positive or negative, it's stable. This is an ion, and it's positively charged because it's two positives and 1 negative, so it doesn't balance out. This electron could fill this hole. And if that happened, if that moved from there to there, you would end up with a hole here, which means that this would now be positively charged. So the positive charge has moved in that direction, and the electron has moved in that direction. And basically, if we have a battery, and the battery works on chemistry, it's a chemical store of energy, but effectively if we have a circuit, imagine I've got a switch here and I close that switch, what's going to happen is that almost instantly, and this is the thing about electricity, we talk about electricity sort of flowing through the circuit, but actually it doesn't just flow as much as everything moves around at the same time. It's like a long chain of people all holding hands. If one person at this end moved, then the person at the other end would have to move. So the whole thing is almost instant. But effectively, what you've got is an electron going into the battery to fill one of these positive holes. So that's the way you can think about it. So now that becomes positive. So an electron from here fills that hole, so that becomes positive. Electron fills that hole, from that becomes positive, and so on. So you can see that the positive charge, if you will, is moving round the circuit. You see? And this is why, when we talk about electricity, although electrons, they're the actual physical things that are moving, and actually this is a hole. Now that's not a physical, it's the electrons moving in this direction that create the actual work or energy or power from the circuit. We visualize it by talking about the positive charge moving around the circuit, and this is to do with the discovery of electricity in the early days, and they didn't know about electrons, but they could see this positive charge, and so they sort of visualized that this is how electricity worked, with the positive charge moving from the positive around the circuit to the negative. So effectively, although we have a positive charge, what we really have is electrons moving around the circuit in that direction, and we refer to this as flow of electrons, and more commonly we talk about something called the current. Like the current in a river, there's a current of electrons flowing through, and the speed and the amount of electrons flowing through the circuit gives us a different value for our current. So current is one of the first important terms that we need to understand when we talk about electricity. Now, when the electrons flow through the circuit, they're likely to encounter, as they go round, different types of material which have, and the second important term, resistance. So the electrons are flowing, draw a couple of electrons, imagine that they're flowing through this copper wire, and there's a limited amount of resistance, so they're having to give up very little energy to move through that material. Then they might encounter a different material, and as they move round, they encounter resistance, so they have to give up energy to get past that resistance. And the effect of giving up energy is heat, and if it's a bulb and it glows white hot with the energy being released, you get light. So this is how electricity does its work. The electrons give up energy through, for example, resistance, to create an effect, an electrical effect of some description. So the next important point that we need to learn is resistance. Now, what makes the electrons move? And we've got a drawing here, or a quick sketch here, of a battery, and the battery has, basically, it's a chemical store of positive ions and negative ions. We don't want to really go into the detail of how this works, just to say that we have chemistry that gives us positive ions and negative ions, and when we connect the circuit, this acts, some people like to describe this as a tank of water. I much prefer to describe it as a sort of pump that's pumping the electrons around. And the amount of pressure, the amount of force with which it can do that, is our third important term, which is volts. So volts was described by a person called Voltaire, hence we call them volts, so it's got a capital V. Resistance was described by a scientist called Ohms, so we have Ohm's law, which we're going to look at in a minute, and current from a chap called Ampere, so that gives us amps. So we refer to the current flowing in amps, that's their units. Resistance is in ohms, we use a symbol for that. And volts is capital V. And we have this very interesting and very important relationship with regards to the volts, the current and the resistance. And this is sort of the key factor in electronics. And this important principle, a sort of balance in the circuit, if you will, we can illustrate with a, if you've seen these triangular formulas, we're going to use a triangular formula to show how Ohm's law works. So we have volts on the top, we have the current, and we have the resistance. And we can explore this by looking at this is the symbol for a cell of a battery. Positive, it's longer there, it's got more, and negative here, it's got less, like some bits taken away. So we've got positive, and we've got negative in the cell. And we've got a circuit in which the current is going to flow, and we're going to have some form of resistance. And this is the symbol for resistance. A straight line, a rectangle box, and another line. So we have here a cell, and we have here a resistor, and we have a circuit, like so. So thinking about Ohm's law, we come to our first sort of analogy, if you will, trying to understand the relationship between the voltage being pumped around the circuit, the current, speed, and the number of electrons flowing around the circuit, and the resistance in various different components. And one of the reasons that we're sort of focusing on Ohm's law and to do with the resistance is, if you can think of all the components in the circuit, the electrons would have to travel through all the different components of the circuit. So all of those components, including the battery itself, will have some form of resistance. So we're looking at sort of what voltage would be needed to pump electrons around the circuit at the appropriate current for things to happen, for the resistance, for example, to be overcome, so the electron could go all the way around. So if we have a resistance, we would need a voltage to pump the number of electrons around as a ratio of each other to establish that is Ohm's law. Resistance is equal to the voltage divided by the current. So if we pick a nice round number, say we have 50 ohms. Okay, so I know the resistance is 50, then there should be an appropriate voltage. I'm going to pick up a battery. Imagine you've got a couple of those. You might have it's a 1.5 volts. If you had two of those, perhaps you'd have 3 volts. The question would be what current would be required. You know, what current could travel through the 50 ohms? So we look at the triangle, and basically this works simply like this. If you want to rearrange things, then you take the voltage, so that I, the current, is going to be equal to V on the top, R on the bottom, so 3 volts divided by 50 ohms. Okay, and you know, you're going to get sums like these that are going to require you to use your calculator to come up with an answer. And so what I'm going to ask you to do before well, I'm not going to reveal the answer in this video. I'm going to come back to this in the next one, and hopefully you'll have worked out what the current in amps is. So from this you need to go and perhaps do a little bit of research on amps and current, ohms and resistance, and volts. In the next video we'll look at the answer to this question.